All. Welcome to online lecture series on Laplace transforms. In this lecture also we'll continue deriving Laplace transform of some elementary functions. In the last lecture we derived Laplace transform of 1 as 1 by s, Laplace of e power at is 1 by s minus a, Laplace transform of sin at is a by s square plus a square, Laplace transform of cos at is s by s square plus a square, Laplace transform of sin hat is a by s square minus a square, and Laplace transform of cos hat is s by s square minus a square. So we'll continue deriving some more Laplace transforms of elementary functions. Let us start now. We'll start with the Laplace transform of t is given by 1 by s square. We'll prove this. We'll consider the definition of Laplace transform, which is given by L of f of t is integral 0 to infinity e power minus st into f of t dt. Now in place of f of t, let us substitute t. Therefore L of t is equal to integral 0 to infinity e power minus st into t dt. That can be written as integral 0 to infinity t into e power minus st dt. Now to derive this integral, let us apply integral by parts here. You know that integral by parts is given by integral of uv is equal to u into integral v minus integral of u dash into integral v dv. So here we take u as t and v as e power minus st. So now if we apply by parts, we can derive it as t times integral of u, that is e power minus st, is e power minus st by minus s minus integral of derivative of u, that is derivative of t is 1, integral of v is e power minus st by s, and again the integral of e power minus st by s gives e power minus st by s square with the limit 0 to infinity. So first if we substitute limit infinity as the upper limit infinity, then we get 0 because e power minus infinity goes to 0 minus. Now if we substitute lower limit 0, the first term becomes 0. The first term t times e power minus st by minus s becomes 0, and second term e power 0 by 1 square gives 1 by s square. So finally we get it as 1 by s square. Therefore Laplace transform of t is given by 1 by s square. Now what is Laplace transform of t square or t cube or t power 4 or higher powers, higher integer powers of t? Let us see that. Laplace transform of t power n is given by n factorial by s power n plus 1 when n is a positive integer. Remember this, when n is a positive integer, that is n can be 1, 2, 3, 4, 5 and so on. It's not a number like 1 by 2 or 3 by 5 or 4 by 5. It's not a fraction, it is a positive integer. So let us derive this. As usual, we take the definition of Laplace transform of f of t given by integral 0 to infinity e power minus st into f of t dt. Now in place of f of t, let us substitute t power n. So that L of t power n is integral 0 to infinity e power minus st into t power n dt. For this again we apply integral by parts, taking t power n as u and e power minus st as v. So if we substitute u is equal to t power n and v is equals to e power minus st in this formula, then we can derive this. See, u is t power n, u here is t power n, integral of v is e power minus st by s within the limit 0 to infinity minus second term is integral 0 to infinity u dash, that is derivative of t power n is n into t power n minus 1, integral of v, that is integral of e power minus st, is e power minus st by minus s dt. Okay, so if you carefully substitute the terms here, you can obtain this equation. Now let us see what happens next. Now if we substitute the limits in the first term, when we substitute infinity, it goes to 0, and because second term lower limit is t power we have t power n term, it also goes to 0. So entirely the first term is 0 plus, why? Because we have minus here and minus here, 2 minus, so it became plus here. N and s are taken outside, so n by s and we remain with integral 0 to infinity t power n minus 1 into e power minus st dt. Now once again come here and look at the definition of L of ft, integral 0 to infinity e power minus st into f of t dt. Now look at this integral. In place of f of t, we have t power n minus 1 here. Therefore, this entire integral is Laplace transform of t power n minus 1. So this gives n by s into Laplace transform of t power n minus 1. So what did we derive now? Laplace transform of t power n is equal to n by s times Laplace transform of t power n minus 1. Similarly, if we find Laplace transform of t power n minus 1, it gives n minus 1 by s into Laplace transform of t power n minus 2. And again Laplace transform of t power n minus 2 gives n minus 2 by s into Laplace transform of t power n minus 3. So if we repeatedly apply this, we get Laplace transform of t power n, which is equal to n by s into Laplace transform of t power n minus 1. And by above, Laplace transform of t power n minus 1 is n minus 1 by s into Laplace transform of t power n minus 2. And again Laplace transform of t power n minus 2 is n minus 2 by s into Laplace transform of t power n minus 3. So if we go on repeatedly substituting this, after n steps we get n by s, n minus 1 by s, n minus 2 by s, and so on, 2 by s, 1 by s into Laplace transform of t power 0. And the numerator is here n into n minus 1 into n minus 2 and so on up to 2 into 1. That gives n factorial, that is n factorial. And in the denominator we totally have n plus 1 s, product of n plus 1 s, that is s into s up to n plus 1 terms, that gives s power n plus 1. And L of t power 0 means 1, and we know that L of 1 is 1 by s. Therefore, we get that as n factorial by s power n plus 1. Therefore, L of t power n is equals to n factorial by s power n plus 1, where n is a positive integer, because when n is a positive integer only we can write n into n minus 1 to n minus 2 and so on as an n factorial. If it is not a positive integer, we cannot denote it as an n factorial. So Laplace transform of t power n, when n is integer, positive integer is given by n factorial by s power n plus 1. If for example, we take n is equals to 2. So L of t square, in place of n, we are just taking 2. So L of t square gives 2 factorial by s power 2 plus 1, that is 2 by s cube. We just replaced n with 2, that's all. Similarly, L of t power 5 is 5 factorial by s power 5 plus 1. 5 factorial is 120 by s power 5 plus 1 is s power 6. Now L of t power 12 plus 1. We have linear property for Laplace transform. So it can be separated as L of t power 12 plus L of 1. And we know that L of t power 12 using this formula can be written as 12 factorial by s power 12 plus 1 plus L of 1 is 1 by s. Therefore, it is 12 factorial by s power 13 plus 1 by s. So, using this formula, we can find Laplace transform of t power n, where n is a positive integer. Then, what is Laplace transform of t power 1 by 2, t power 3 by 2? It cannot be definitely 1 by 2 factorial power s power n plus 1, that is s power 3 by 2, because we cannot apply the previous formula, because here 1 by 2 is not an integer. Then how do we derive Laplace transform of t power a, where a is a real number greater than minus 1? So let us look into it now. Before that, we'll define gamma function. So let n be a positive number. Then the gamma function is defined as gamma of n is equal to integral 0 to infinity e power minus x into x power n minus 1 dx. And we have some interesting properties of gamma function. First and foremost one is gamma of 1 is 1, gamma of 1 by 2 is given by root pi, gamma of minus 1 by 2 is equals to minus 2 root pi, and gamma of n plus 1 is n times gamma of n when n is a positive number. Gamma of n plus 1 is equals to n factorial if n is a positive integer. And gamma of 0, gamma of minus 1, gamma of minus 2, gamma of minus 3 and so on, these are not defined. Gamma for negative integers and gamma at 0 are not defined. So we use this gamma function to derive Laplace transform of t power a. Now Laplace transform of t power a is given by gamma of a plus 1 by s power a plus 1 when a is a real number greater than minus 1. So to prove this, again we consider Laplace transform of f of t, which is equal to integral 0 to infinity e power minus st into f of t dt. In place of f of t, let us substitute t power a. Then the integral is integral 0 to infinity t power a into e power minus st dt. Now to derive this integral, we substitute this st is equals to x. So put st is equal to x. Then differentiating both sides, we get dt is equal to dx by s. Now substituting all this in the above integral, we get L of t power a is equal to integral 0 to infinity. T power a becomes now x by s whole power a, because t is equal to x by s from this. And e power minus st becomes e power minus x, and dt becomes dx by s. Now s power a into s becomes s power a plus 1 in the denominator, that can be taken outside. Then we get 1 by s power a plus 1 integral 0 to infinity x power a into e power minus x dx. That can be written as 1 by s power a plus 1 integral 0 to infinity e power minus x into x power a plus 1 minus 1. This x power a is written as x power a plus 1 minus 1 dx. We added and subtracted minus 1 here just to express that as a gamma function. So now if you look at this, we get 1 by s power a plus 1 into this integral becomes gamma of a plus 1, because gamma of n is integral 0 to infinity e power minus x into x power n minus 1. Now in place of n here, we have a plus 1. In place of n, we have a plus 1. Therefore, it is written as gamma of a plus 1. Therefore, L of t power a is given by gamma of a plus 1 by s power a plus 1, where a is a real number. So now L of t power 1 by 2 is gamma of 1 by 2 plus 1 by s power 1 by 2 plus 1. So we can derive Laplace transform of L of t power any fraction using this formula. Now these are the list of Laplace transforms of elementary functions so far we have derived. I am just putting it in a list. L of 1, L of k, L of e power at, L of e power minus at, L of sin at, L of cos at, L of sin h at, L of cos h at, L of t, L of t power n when n is a positive integer, L of t power a if a is a real number greater than minus 1. So one should remember these Laplace transform of elementary functions to go further into this topic. So we'll stop this lecture here, and we'll continue to we'll solve some problems on these using these elementary functions in the next lecture. Thank you for watching this video.